Uh, Also, while others might still be joining, we'll start now to stay on track. And my name is Sandra Kolaric. I am Dissemination and Communication Manager at Foodscale Hub, one of the partners in the STELAR project. And I want to thank you for being here today. I am pleased to welcome you to the STELAR Project Virtual Open Day, organized in collaboration with VISTA, our consortium partner leading the pilot on early crop growth predictions. As the STELAR project enters its final phase, we are hosting a series of open days to highlight practical use cases and encourage discussion around digital transformation in agriculture. Now, let me just quickly walk you through today's agenda. You will first hear from Dimitris Skoutas, STELAR project coordinator, who will give an overview of the project, its aims, key challenges and objectives. Next, Silke Migdal will introduce VISTA's role in the project, followed by Salvik Blacher, who will present their work on remote sensing within the STELAR pilot. After that, we will hear from our consortium partners, Eindhoven University of Technology, Athena Research Center, and the University of Bundeswehr Munich, who will share their approaches to field delineation, crop classification, and time series processing. Please stay with us until the end when we will open the floor for a Q&A session and ask you to fill out a stakeholder interest survey. Before we hand over to Dimitris, just a few quick notes. As you've seen, the webinar is being recorded. Please keep your microphones muted when you are not speaking to avoid background noise and distractions. And as mentioned, we will have a Q&A session at the end, so feel free to drop your questions in the chat as we go along. Thank you, and let's get started. I will just stop sharing, and Dimitris, please go ahead with your presentation.
Thank you very much, Sandra, for the introduction and for the organization. Let me share my presentation. So first of all, I would like also to welcome everybody and to thank everyone for your interest in the project. As Sandra mentioned, I will provide a brief introduction. So my name is Dimitris Skoutas. I'm a researcher at Athena Research Center and the coordinator of the STELAR project. I will very briefly say a few things about the project just to provide a big picture, and then we will go into the more detailed presentations about the work that is being done in this context. So starting with some basic facts about the project, the full title is Spatiotemporal Linked Data Tools for the Agri-Food Data Space. And it is a project funded by the European Commission under the call for technologies for data management. So our focus, as you can see, is on data management tools. The duration of the project is 36 months. It started in September 2022. So actually we're getting now close to the end of the project. Also here you can see the list of partners. We have 9 partners from several different countries with a balanced mix, including both academic partners and partners from industry. And also you can see the link to our website where you can find more information about the work we are doing and the results. Regarding the challenges that we are trying to address, our focus here is on data preparation for machine learning and AI applications. And this is a very important part that is often neglected. However, data preparation has a significant impact on the quality and the successful application of these kind of models. And it involves several steps like data discovery, data integration, and data readiness, like annotation and so on. And all these steps pose several challenges that are quite important in this end-to-end pipeline. So how to find data that is relevant and appropriate for the task at hand, how to combine data from different sources, aligning their schemas, their spatial or temporal resolutions, and so on, how to automatically label data if labeled data sets don't exist, how to detect and mitigate bias, or to perform data augmentation, and so on. These are the types of challenges that we are trying to address in the project. And our vision is to develop a so-called knowledge lake management system, KLMS, which essentially has two main pillars. On the one hand, the platform, which contains several core components for discovering and managing datasets and workflows that contain tasks operating on these datasets. And on the other hand, a toolkit that contains several tools that address these different steps in the pipeline that I mentioned about data description, linking, and annotation. With some more detail regarding the platform we have been developing, the focus here is on metadata. So typically what the data scientist does is to create workflows that may comprise one or more steps of data preparation actions. And typically these steps use various algorithms or models, and each one of them has different configurations, different parameters, and produces different metrics. So there is a need to track these executions of such workflows in order to optimize and debug them. And this is what the platform tries to automate the collection of this type of metadata and comparison of different configurations in order to guide and support the data scientist to design better workflows. In terms of individual tools, we have a range of tools covering different functionalities. For example, for data discovery, we have developed a data profiler that enhances dataset descriptions with more information, as well as a synopsis data engine that makes it easier to handle very large volumes of data. For interlinking, we have tools that match entities or schemas from different sources, or align time series with different temporal resolutions, and also identify correlations and so on. And for annotation, we are focusing both on text data, where we provide tools for extracting information, as well as on tools that operate on satellite images to perform field segmentation or crop classification. And in order to test these tools, we have 3 pilots in the project. The first one focuses on risk prevention in food supply lines, where mainly we're dealing with textual data, and we're using different tools, including Gen AI techniques, to extract important information like food products or hazards. In the second pilot, which is also the focus of this of the next presentations, our goal is to provide tools for early crop yield prediction, which can operate both at a local level to support farm management, as well as on a global scale to support applications, for example, related to food security. And in the third pilot, we are focusing on precision agriculture scenarios, for example, developing algorithms for constructing suitability maps based on several types of variables. So this is, as I said, a very brief overview. We will focus here on pilot B, and I will hand over to my colleagues to describe this in more detail in the next presentations. Thank you very much again.
Thank you, Dimitris. As mentioned earlier, Silke will now give us a brief overview of VISTA.
Thank you for the introduction. I hope you can see my screen. So yeah, my name is Silke Migdal. I'm one of the 2 managing directors at VISTA, and we lead pilot use case B. So who are we? We are a remote sensing value-adding company who focuses on the water, food, energy nexus. So what we do is we provide services derived from Earth observation and enhanced with modeling for this complex area where water, food, and energy intermix. We do this on different scales. Come on. We do this on different scales. one that we're going to talk about a lot here today is our harvest and yield prediction monitoring, which is something we do both on a field scale, so see what individual fields do and how they're doing, and also on a large scale. Like here you can see a yield prediction for all of Europe, which can then with aggregation levels of different types from like individual townships to whole countries. We also have services for site-specific farming, so for precision and smart farming, where we really derive the differences in the fields and give farmers information and recommendations about how best to irrigate, how best to fertilize their fields, to make sure that the input resources are used as efficiently as possible and the output is as stable as possible. We do crop monitoring and risk management. So this is something that is also usually done on a larger scale to see how, for example, do dry spells, droughts, how do they affect the plants? But also the opposite, what happens if there's too much water and not enough sun? How does that put the plants at risk, so that we can really also see how is everything developing in the lead up to the harvest. And last but not least, we also have a big focus on sustainability and carbon farming. So here you can see a soil organic carbon content map, where we derive from Earth observation all kinds of different indicators for sustainable farming, and to make sure that all of the sustainability goals, ESG goals, are reached. How do we do this? We use mostly optical satellite data, and since I don't know how much background you have for this kind of data sets, I just wanted to show you a few. We use a lot of Copernicus data. This is the European constellation, and here mostly Sentinel-2, which is a optical sensor that has a wavelength range from 400 nanometer to 2200 nanometers. So from the visible to the near infrared and then the shortwave infrared. And these different wavelength regions can show us different things. You can see this on the right side here, where you can see different plant absorptions and reflectances. So chlorophyll concentration, for example, is something that you can see mostly in the visible, in the green and red. The leaf area is something that you can see in a wavelength in the near infrared, where our eyes cannot actually see. So this is something that we derive from the satellites, that our eyes as such cannot see. Different wavelength spectra have different information, as you can see, so we're using all of them. We use mostly physical modeling with just some deep learning and machine learning on top of it, because we know a lot about how the land surface processes work. We know the radiative transfer of the on the land surface as well as the one in the atmosphere, which means we can correct for this. So we have large processing chains that we mostly developed ourselves, but we take the optical satellite data and then correct for atmospheric disturbances, classify clouds and cloud shadows, classify the land use, and then finally retrieve crop parameters like the leaf area, which can then be input to all of the other analysis. For this, we use both our own in-house computing facilities as well as also a lot of cloud processing. Just to give you an example of how much data this really is, because this is all really big data handling, our storage, which we have at a local computing center, that is 2 petabytes of data now. So that is really a lot. How does this look like now if we look at the time series? So you can see here a time series from early spring to summer north of Munich. You can see how the fields change in the visible spectrum. So this is more or less like we would see it with our eyes. You can see, for example, some yellow fields popping up. This is when rapeseed is blooming. So then we have a lot of yellow in there. And we can see how the fields are developing. Now, if we take a few winter wheat fields here and look closer at those, and we do all of these steps that I told you about before and derive leaf area, you can see here the 3 different temporal developments of leaf area. So you can see the fields are really quite dissimilar. Some start earlier with their growth, some have a lot more leaf area than the others. And then I plotted for you also the yield at harvest. And you can see the development of the leaf area, the one that has the highest and earliest development also then has the highest yield in the end. So this gives us a lot of information. It gives us basically the complete growth of the plant over time, which we can then use to derive the yield in the end. And for this, we have the ProMed model, which is also a physically based model, where we can simulate the crop growth, the yield, and all of the relevant land surface processes, and also under many different agricultural management alternatives. You can see on the left how winter wheat phenology over all of Europe is modeled. And in ProMed, you can see, even if you maybe can't read the actual dates, but you can see it always starts, or it starts this year in the southwest of the continent, and then slowly the winter wheat starts also growing further north and further east. ProMed is a complex model. It has all of the necessary cycles, the energy and water cycle and the carbon and nutrient cycle that it models, which means that it can also really be transferred and adapted very well to different areas, which is also very nice. And now when we use this model, we can use it in a standalone way, but there are always things where a model has to generalize. There are local hailstorms, some farming management that we don't know. All of these things the model cannot incorporate. So we incorporate that via the satellite data, because as we saw, the leaf area has a big influence on the yield. So what we do is we run the model, we run different scenarios. It is driven by the meteorology. So by all of the weather, how much precipitation, how much radiation, how much sunlight is there. And we do this until we have the first satellite image. And at this point, we know how the leaf area on the field looks like. So that works as a sort of lens. It focuses things. So we can start from that point again and keep calculating our scenarios. And we do this again and again. And always when we have a new satellite image, we assimilate this into the model. And then over time, we get a very, very clear picture of how the crop developed over time, and can then, via this assimilation process, get very, very accurate yield forecast. Here you have an example of a yield forecast for just 2 fields, and you can see on the right side the yield map as it was measured by a combine harvester. So directly on the field, and you can see there are a few differences, but mostly both the absolute values and the patterns are very similar. We have then built on this technology to have our Epsilon service, to develop our Epsilon service yield prediction from satellite, which is this European-wide yield forecast system for wheat, barley, maize, and rapeseed, where we have already quite a good success for 4 to 6 weeks before the harvest. We can get good yield results. You can see we have validated it for many years and many and all the different crop types. But now we want to go a step further, and this is what we're doing in STELAR. We want to have these yield forecasts even earlier in the year, so that we can see how early can we actually get and still have a very good correlation. How much early warning can we give? Is it possible to go to a point where there's still management that can be done on the fields to make things better, to even have a yield forecast at that point? And all of these details on what we're doing in STELAR and what tools we have developed to make this happen will then be shown by my colleagues. So I stop here and give on to my colleague Solveig. Thank you so much.
Thank you, Silke. Solveig, we are now ready for your presentation on the pilot's technical developments.
Thank you. All right, let me share my screen. Okay, you should be able to see my presentation now. Thank you for the introduction to STELAR the project and to VISTA as a company. I'm Solveig, I'm the project scientist at VISTA, and I do the internal lead for STELAR within the VISTA company. So today's open day will continue on what we showed you on the first open day, where we focus really a lot on the outcomes of the pilot itself. And what happens today is that I'll give you some intro to the pilot, to the results that we generally had, but then the better part of the focus will move on to the tools themselves. So to give you a little bit of context, the pilot had two main challenges. So one thing is that modern agriculture requires consistent information for decision-making processes, which means we need spatially and temporally accurate data. So the more data that we have, the better our predictions become. And the second thing is that plant growth is highly dynamic, especially in phases of the LAI maximum. So the flowering of the different crops, that's one of the time points where we need the most amount of information, because that gives us an idea of how well is the crop doing, what kind of yields can we expect, is there anything that we need to know to manage agriculture better in terms of irrigation, in terms of fertilization, and so on. So we need data with a good spatial resolution, we need data with a good temporal and spectral resolution to manage all of this. Within the pilot, we have two use cases that demonstrate two parts of this, essentially. So we have the first use case that really focuses on, similar to what we do at VISTA already, to data processing done on single fields, on small, on farm level, essentially, which also means that we already have field boundaries. So we have a lot of known facts. We have the boundaries. We know the crop type. We know things like planting date. And we can usually talk to people to get a bit a sense of the information that we can get from farmers, which means we can really dig deep. We can use tools that are more computationally expensive because we don't have to process that much data, and we don't need to go digging for information within the data as much. The second use case focuses more on food security and early warning, which means we go to a much larger scale. We want to do yield predictions at a sub-national level, which also means that we need to go look for our crop types. We don't know the field boundaries, so whenever we want to sample data, we don't know where exactly to look for the data. And also this means we have a lot more data to deal with in the beginning, and that has to go through processing chains, which means we also have a little bit of a trade-off between getting a lot of accuracy, but also using any kind of algorithms or any kind of methods that are close to state of the art. The tools that are being used within the pilot are four, to be exact. So we have the data fusion, we have the time series imputation, field segmentation, and crop classification, which all of them they leverage different types or different parts of data that comes from satellite, so data that comes from Earth observation. We use multi-sensor information, we use time series information, we use spectral information. And all of this eventually leads to a better time series, a more complete time series, to eventually do yield prediction a lot earlier than what we're currently doing. The data that's being used comes mostly from optical data from Sentinel-2A, Sentinel-2B, Landsat 8, and Landsat 9. And from all of those four sensors, we get leaf area index, which is essentially a proxy for biomass for plant health and for other plant biophysical parameters. And the leaf area index itself comes from spectral information, but we also use the spectral information, for example, in the field segmentation part, which you'll learn something about later on. But what is really relevant here is that even through the season, when we see, like in the figure on the right, we can see the plant development over time. And we can also see that during the LAA maximum for different crop types, we see different patterns in the spectrum. So what you can see here is essentially the spectrum from Sentinel-2, or Sentinel-2A and B. And the columns here, the blue, green, and red, are the wavelengths that we can see with our own eyes. Everything else of that data we cannot see. That is what we use the satellites for, because beyond the spectrum that we can see, the spectrum tells us a lot more about the plants themselves. So we've got the near infrared, we can see a lot about plant structure, leaf structure. And this is also where we can see a lot of differences between crop types, which is also very relevant information, because yield prediction is always done crop type specifically. Just to give you a short overview of a study area. So generally for the smaller use case, the use case 1, we collaborate with farmers in Germany, where we get information on different crop types, the field boundaries, the yields for different years. And as for the second use case, we go to larger regions in Austria and France that cover a different amount of Sentinel-2 tiles. So Sentinel data is always provided in a tile format, so essentially large photographs of the Earth. And with that also means that for the France data, we have to process a lot more data than for the Austrian data. And in those areas as well, we want to do all of the processing for multiple crop types. To give you a quick run through of the first use case. So the first run through went on to 6 winter wheat fields in the central Germany, in Hessen and Germany, where we processed 44 hectares in total. And we used LAI data from Sentinel-2A, 2B, Landsat 8, and Landsat 9. And the time series that we got from that data, at least in 2021, consists of circa 50 time points within the time range of February 10th, 2021 and August 30th, 2021. And just give you an idea what the results actually look like. We have the reported yield for different fields, and we have the yield that came up from the STELAR results from the STELAR tools. And I'd just like to show you a little bit more about why this changes a little bit, because as I said, crop growth is a highly dynamic process, which means we have a lot of in-field changes in the season. We have a lot of differences between the fields depending on planting day, depending on the exact, not it's just the crop type, but the sort of crop, because even within the winter wheat, we have different kinds of winter wheat. And what you can see here in the time series plot is the LAI time series for all of those fields on the bottom in 2021. And you can see that in the early start of the growth season, we have a lot of in-field differences, which means the plants develop differently within the field. When we go more to the LAI maximum, there's a lot less heterogeneity. So the plants are at full maximum, at full bloom, and more or less around the same time. When it comes to senescence, when the crops are maturing, we go back to having a little bit more heterogeneous data in the fields, which also means that the end yield is usually quite different. As for the second use case, I'll talk a little more about the data that we got from Austria. So we again focus a bit more on winter wheat in this case. We had 6,000 winter wheat fields detected, which all lie in a low elevation corridor in Austria, which means it's bordered by the Austrian Alps and by in the south and by the Bavarian forest in the north. The time series for these kinds of data, they consist of 47 time points in the date range of February 7th, 2023 to August 30th in 2023. And here again, we used for the time series LAI data from Sentinel 2A and 2B, Landsat 8 and Landsat 9. The detection of the fields itself was done on Sentinel 2A and 2B spectral information because they were fine there. As for the results, just to give you an idea of what these look like, the yield for Upper Austria was 5.72 tons per hectare, and for parts of study area in France, it was at 4.91 tons per hectare. And what I'd like to kind of give you a bit more information on is phenology and LAI, because the phenology describes the plant development and maturity, but the LAI gives you an idea about how well the plant actually is, how does it grow, how do the different plants grow within an area, because even in a region as small as Upper Austria, we still see a lot of differences. Like we have the same crop type, we have similar soil conditions, we have similar meteorological conditions, but we can still see that getting to the point of having very good time series, having a distant time series is still very complex even within a crop type. So to sum everything up, we applied full tools from the STELAR toolkit in the first iteration of the two use cases in regions that show very different environmental conditions. So we have areas where we're very close to the mountains, which means we have smaller fields. We have different meteorological patterns influencing crop growth conditions. We have the proximity to the sea that again comes with other kinds of challenges. We have different observation geometries of the satellite due to the elevation changes or the elevation differences in Austria, and especially when compared to France. And what we also did was to demonstrate more the kind of challenges that we have in agriculture at two very, very different scales. And this is more or less the quick sum up of what happened in the pilot. So with this, I'd actually like to pass this on to the next presentation, which is the field segmentation, I believe, from TU Eindhoven.
Thank you, Solveig. Now Jens Dont from Eindhoven University of Technology will share insights into field delineation.
Yes, thanks Solveig and Voetskilhoop for the introduction. So my name is Jens Dont. I'm a researcher here in Technical University of Eindhoven, which is one of the academic partners in this project. And specifically, me for TU Eindhoven, I'm helping VISTA with the task of field delineation. To kind of provide the concept of field delineation here, we have a kind of a schematic overview of the pipeline or workflow of what we're trying to accomplish within the STELAR project based with the data from VISTA. So kind of the end goal here is to be able to do a yield prediction at either a field or a subfield level, such that we can earlier, if that prediction turns out to be bad, that we can warn the respective farmer earlier and take corrective action. Now, to be able to do yield prediction solely based on kind of the development of a crop over time, we get a data structure called time series, which are data points over time. However, you can imagine that at the scale which VISTA works, the satellite data, if we're talking, these images are not the size of a simple profile picture. These are images of potentially millions or trillions of pixels. And now, if you would do this analysis on a pixel level, then all these tasks such as time series extraction, but also imputation and yield prediction become very, very computationally expensive, meaning that they will take a lot of time. So one way to kind of battle that computational complexity is by working on a field level rather than on a pixel level. So this here is an example of just a very, very small part of a satellite's image provided by VISTA. And you can imagine that one of these fields already contains about 200 pixels. If we can, but that field itself, it has the same crop. It likely has the same crop type, and the crop is likely also impacted by the same environmental factors. So if we can reason on that on a field level, it would make the whole process a lot easier. Earlier, I think Solveig talked about that there are also a lot of these field boundaries, so which essentially is a map saying in an image, this is a field and this is a field. We have it for a large part of Europe, but not full Europe. Sometimes these field boundaries are simply not present. So what we then want to do is we want to be able to generate these crop boundaries automatically. And that's what this task is about. It's about automated field delineation. And just a small teaser here, how we solve this problem is by training a neural net, a segmentation model on VISTA satellite data. So actually the images that you and I can also see, to be able to output these boundaries that you see in red here. So that is in a nutshell the problem statement of this task, automated delineation of fields from satellite images. However, there are a few quite big challenges here. In an exploratory study in the beginning of the project, we first experimented with classic computer vision techniques, like filters and edge detections, but those seem to be very dependent on the lighting conditions and also a bunch of factors of the image itself, which made that it worked good in some cases, but it also worked very poorly in other cases. So an alternative approach we then went with is to train a deep learning model, which is able to hopefully generalize better to different areas, to cope better with different lighting conditions, and to generally just result in better boundaries. Specifically, what we did with this model, or something we were very lucky with, is that one of these field delineation models was already developed as part of an earlier EU project, which specifically the project NIVA. It didn't provide the model, the trained model itself, but it kind of provided the architecture, or let's call it the scaffolding, for us to build one of those models ourselves. So we took the code from the NIVA project and we retrained it on a large data set, the AI for boundaries data set, which is essentially the same data that VISTA used, so Sentinel-2 data, but using known field boundaries in order to train a model. And one thing that the model then outputs, so it takes in an image, an RGB, so red, green, blue image, and it outputs three different things. It doesn't only output the boundary predictions, it also outputs predictions on what it thinks are fields. So for every pixel, it gives a prediction, is this a field, yes or no? And it also outputs for every pixel a value predicting how far away this pixel is from the boundary. Now, initially one would say, why not only output the boundary prediction? Well, research has showed that if you train a model to output these three kind of connected statistics, it will at large provide better results, and the boundaries itself will look more like fields. If you would only do boundary prediction, what you usually see is that the model only works on a pixel basis and the fields will get very weird shapes. Now, so we trained this model, and now that we have this model, we can take in an RGB image and it output, and we can combine the predictions of extent, distance, and boundary here in order to merge them together into what we call a final boundary prediction value, which means that for every pixel in the input RGB image, we will get a value from 0 to 100, where 100 means it's very, very certain that this pixel is a boundary, and 0 means it's not. And then on that new black and white image, you can kind of see it as we then perform through classic computer vision techniques. We perform edge detection to obtain a map of these field shapes similar to what VISTA has as ground truth field maps, so that we can essentially just plug it into existing pipelines. If we have a ground truth data set of a field map, then nice, then we know for sure that the fields are good. If we don't have it, then we will perform automated field delineation to get that field map ourselves. Now, just on a more technical note, this is what the pipeline looks like for automated field delineation. First load in the RGB image. It's actually a 4D matrix rather than a 3D matrix, because we don't only have red, green, blue, but we also have some infrared information in there, because we found that that would actually improve the field prediction as well. Because these input images can be very large, we split them up into smaller images such that we can process them more efficiently in our segmentation model. Then for each one of these splits, or patches as we call them, we segment it. We combine the boundary, extent, and distance predictions into a single boundary prediction, which is the middle image you see here. Then we use vectorization, which is a classical computer vision technique, to obtain a shape, like a list of shapes for a certain image. And then, because we are still working on the patch level here, we then combine the shape files from every patch into a single shape file for a specific input file for VISTA. And that gets then passed on to the other modules in the pipeline, like time series extraction and time series imputation. So that in a nutshell is what we did for field segmentation. If there are any questions in the end, I'm happy to answer.
Thank you, Jens. Next, George Marinos from Athena Research Center will walk us through time series processing.
Hi, everyone. Let me first share my screen. Can you hear me well, right?
Yes.
All right. Just a moment. Okay. I'm George Marinos. I'm a research engineer in the Athena Research Center, and I'm going to present the time series imputation part module of STELAR project. Regarding a few words of the presentation outline, I'm going to talk about generally time series imputation, what we are built here during the STELAR project, the TS Impute tool, our last developments, and then we'll give some example pipelines of our last developments, and we will share, of course, some results that we observed during our experimental setup. So a few words regarding the time series imputation task. Time series imputation task is one of the 4 fundamental subtasks in time series analysis. As you can see in the slide, the other ones are forecasting, classification, anomaly detection, and pattern recognition. Like it is mentioned in the reference at the end of the slide, imputation is generally important and can be very effective as a prerequisite for meaningful analysis for downstream tasks like forecasting and classification and so on and so forth. So that was the intuition behind this module. to use time series imputation in order to improve the final downstream task, which would be early crop yield prediction. So dive into more details in the specific domain in agriculture. We have leaf area index values in the form of time series, like Solveig in her presentation mentioned before. And in those time series, because of several factors like cloud cover, sensor malfunctions, irregular observation intervals, and so on and so forth, we might observe missing data. And our task is to try to reconstruct the missing part of the series in order to finally have better early crop yield forecasting. And during this task, we investigate whether or not, and if yes, in what extent, missing value imputation improves crop yield forecasting. A few words regarding our tool, which is the TSMP tool. We cover all the 3 generations of methods of time series imputation, starting with the first generation of machine learning based methods, which consist of classical statistical and tree-based models. The second one is the state-of-the-art deep learning-based methods, with most of them are very well known, like SITES, TimesNet, and so on. And the last developments that we added to our tool are the LLM-based methods that built upon transformer-based methods and are based on pre-trained large language models like Llama and Mistral. And we aim there to utilize those pre-trained LLMs that have some knowledge of the world to better impute the time series. To give you a better intuition of what we are doing, this is a prompt example. We do a lot of prompt engineering. And like everyone does nowadays with ChatGPT, we construct a prompt and we give it to the LLM and we receive an answer, starting from the very basic methods like zero-shot prompting, where we just construct the prompt, give it to the LLM, and we receive an answer, and moving on to more sophisticated methods like few-shot prompting, either with random examples or using retrieval augmented generation, which is one of the state-of-the-art recent developed methods in the literature, where we retrieve similar time series and end up with having other methods like multiple choice prompting, where we run several deep learning algorithms and construct a prompt based on a multiple choice question, where we ask the LLM to choose the best of this one. We cover a range of different prompting methods. Here we have the example of few-shot using retrieval augmented generation pipeline, where we start and looping over the missing values in the data, the ones that we would like to impute. The user has the ability to specify a time range in order to the imputation to be done in that specific time range. Otherwise, we impute all the missing values in the dataset. We move on by retrieving k-similar series. The k number is again defined by the user, and the major component here is the vector store creation, where we have the whole dataset of time series. We do feature extraction, and we index the time series, and then we are able to retrieve k-similar time series based on a similarity measurement. And we use, for example, Euclidean distance, but it might be cosine distance or anything else. And then once we retrieve the similar series, we construct the prompt and give it to the LLM, hoping that the similar time series, the examples that we constructed with this more sophisticated way, will help the LLM understand the connections between the other points and the missing part, and we receive a better answer. In the other example pipeline that we have listed here with a multiple choice, this is a hybrid example pipeline. We start and again looping over each missing value in the data. And then we run K state-of-the-art deep learning models, like, for example, sites, TimesNet, CSDI, and anything else. And we collect the results. And for each specific missing value, we construct a multiple choice question where we ask the model to choose one of what it thinks is the best for the imputation. If we give him, of course, the whole time series and with the missing parts. The intuition here is that the LLM acts like an ensemble model, where an ensemble model would be able to collect all the knowledge and the forecasts of other trained algorithms. And then we construct the prompt, we give it to the LLM, and we ask for an answer. Here's an example of the prompt of the last case that I talked about. Here you see, for example, that we have run linear interpolation, sites, TimesNet, CSDI, and this is for a specific part, for a specific missing value in one leaf area index value time series. We construct the prompt, we give the whole time series to the LLM. We also give the prediction of each model. And we enforce the LLM to either select one of the forecasts of the other algorithms, or do its own estimation if they think it will be better. You see here the answer that the LLM response was a specific number, a specific float number for a specific date, and we also have the ability here, the inherent ability of the LLMs to request for an explanation. Here you can see that compared to the other state-of-the-art deep learning algorithms, the LLM made a closer forecast. The linear interpolation, it was good as well, and it was better actually. But in this specific case, LLM outperformed the other deep learning algorithms. And this is my final slide, where we present some of our preliminary results for a small-scale experimental setup, where we have, for example, 10 number of runs with a different number of fields, leaf area index time series in each run, and we experimented with 10 series, 20 series, and 500 series. And we, of course, included all missingness percentages from the range being from low to high. And for all crop types, grain maize, winter wheat, sunflower, and winter barley. And you see here that, again, in this small-scale experiment, linear interpolation also has very good results, because this is most probably due to the factor that most of the series has a smooth pattern. But in this small experimental setup, LLMs performed very well. And for these specific measures here, mean absolute error and root mean square error, actually outperformed sites and TimesNets in most of the cases. So this is insightful. Not all the cases are the same. So in other cases, deep learning algorithms might outperform LLMs, but this is the case that we investigate whether or not and in what extent LLMs can be better, and under what circumstances from the state-of-the-art deep learning models that need to be trained. Because the major advantage of the LLMs are that they do not need training, because they are already trained. So that concludes my presentation. I would be happy to answer questions in the questions time. Thank you.
Thank you, George. And now Chetan Krishnamurthy Ramanaik from the University of the Bundeswehr Munich will present their work on crop type classification.
Hello, everyone. My name is Chetan, and I am a research assistant at the University of Bundeswehr at the chair of open source intelligence, headed by Professor Irinu. So I will be presenting bias-aware crop classification. So we have the data, LAI data from VISTA for the crop type classification, and we have some challenges in the data set, including the bias due to cloud coverage. And we have the ground truth from Eurocrops, which we had to map to the LAI provided by VISTA. And we see that the crop types are also imbalanced. And so to start with data preparation, we have LAI from VISTA, which is a large landscape of, in the image form, it's around 10,000 cross 10,000 pixels, which had to be sliced into required spatiotemporal patches of size 64 cube, which I'll be explaining later. And we do the training, experimenting with several deep learning models, and we found that the 3D unit was a suitable model. And we do the inferencing, examining how the bias factors like cloud coverage and crop type imbalances are affecting the results. And based on that, we propose bias mitigation measures, which includes some post-processing techniques and sampling methodologies in the training data, which we'll be explaining later. So this is an overall pipeline. I'll go into some details of these steps. So firstly, as I already told, the LAI provided by VISTA is a time series image dataset, which you can see here. Is a small patch of land in time series with a lot of gaps in the middle due to cloud coverage. This is how a training sample looks like, an input data. And this is the image of all the labels extracted from Eurocrops for the crop types. Every color indicates specific crop types out of all the 41 classes listed by VISTA, aggregating 100 crop types, which are of importance for the predictions. And then we experiment with deep learning setups and to just have a look. This is how a crop mask looks like for a given input. And so overall, the size, how the input data looks like is a number of time sequences and the spatial coordinates. I mean, a 2D image in time series is our input. So to talk about the model, we consider a 3D unit because of the spatiotemporal nature of our data. Our data is a sequence of time series LAI images. So we have to capture both spatial and temporal informations, and how the 3D unit does is through the 3D convolutions across the spatial and temporal dimensions. And we perform a post-processing technique in order to mitigate the effects of cloud coverage, which can lead to missing values in the output because there are missing values in the LAI. So the post-processing involves conversion of the 3D output to 2D, and in the 2D output, the 3D output is processed in a way to mitigate the missing values in the outputs. Considering the confidence values, we get an output image, which you can see here. This is the ground truth and the prediction, which is almost similar to the ground truth, and we get the crop types in the legend for the given color of the crops. And so this is one of the methods of in the post-processing to handle the bias due to cloud coverage. And we have bias within the data, which is due to very imbalanced representation of the crop types. If you look at this distribution, this is how if you plot a distribution of the crop types using the Eurocrops labels, and if I randomly sample the data from this, I may very likely miss out on a large number of crop types in my training set. So we will have to do a conditioned sampling, which is aware of the representation of a given crop type. Every crop type has to be sampled based on its uh, representation, so that we have a good representation of every crop type. And also the sampling should be in such a way that the crop types which are represented not so much should not be oversampled to an extent that um, the model just overfits over the underrepresented crop types also. So this is a sampling strategy to mitigate the effects of imbalanced crop type distribution on the outputs. The other part is how we train the model is through ensemble. We do not consider one single big model to train over all the crop types to predict them using LAI. We consider several ensembles depending on their seasons. To just quote something from a recent publication, they say that smaller models can output larger ones with proper training and ensemble techniques. So we consider 4 different ensembles for 4 different seasons. The seasons were created based on the data provided by VISTA and about the existence of crop types in different seasons. The crop types were aggregated based on their co-occurrence for a given season. And within the season, we don't train the single model for all the crop types. Even there we have the ensembles which are specialized to predict different crop types, and the results are stacked over and finalized based on their confidence values of the prediction. So to just have a look at how our results look like, you see the input time series and the predictions and the ground truth. If you look at this result, in this given patch of land in the input, we have 2 crop types, and this is how the model predict. Even though it misses out on some details, it does prediction to some extent. And similarly, the other examples. And to have a look at the qualitative results, here in this I'm showing a few crop types and not including all the crop types which are still underway in the training. So here these are the distributions of prediction performance of the model for every crop type. And IOU and F1 score are the metrics of calculating the performance. So roughly in both the distributions, higher is the distribution towards the value 1, better is the output. So we can see this is the prediction performance of the model. And also I'm showing a confusion matrix for the crop types. So here you can see in the diagonal shows how much the crop types are predicted accurately. So if you look at potato, the diagonal where have potato as true label and potato as predicted label in shows how much how much pixels are predicted accurately for this, and the off diagonal things are wrong predictions, which are minimal. And due to our ensemble technique, we avoid the wrong predictions in these regions. Because of the ensemble techniques, we constrain them only to these regions. And some more results to show the quantitative outputs. So similarly, like I showed earlier, how the outputs are. Here I'm not showing the input LAI, but just the prediction and what was the expected ground truth. To summarize, we did extract the labels from Eurocrop dataset and map them to the LAI coordinates provided by VISTA, and considering a 3D unit, we developed a spatiotemporal bias-aware crop type semantic segmentation model. And as I already told about the post-processing techniques and sampling techniques, we try to mitigate the bias effects to some extent. So this concludes my presentation, and I'm happy to answer the questions. Thank you.
Thank you, Chetan. Before we move on to the final part of today's session, I will give the floor to my colleague Tatiana, who will introduce you to the stakeholder inter-survey. Just a second.
Thank you, Sandra. Okay, as you can see here in the slide, you can scan the QR code here, and it will take you only 1 minute to provide you your feedback on your interest in STELAR KLMS and the specific services that you heard about today. Also, if you have any comments or you would like to hear more of us, to receive demo or something, you can also put your comments there in email, and we will keep in touch. So your feedback is very valuable for us. Thank you very much.
Thank you, Tatiana. Now we will open the floor for the Q&A session. And just to see if there are some questions in the chat. Please feel free to either post it in the chat or unmute yourself and ask directly. Okay, we have one question. Nicholas, how do you derive the LAE physical or statistical model?
I can take this one. So we derive the LAI from a soil leaf canopy model. So we do this by using a radiative transfer model. So it's a physical model.
Thank you for your answer. Is there maybe more questions? If there are no further questions at the moment, you are always welcome to get in touch with us through the STELAR's website. We have a contact form, and we can forward any inquiries to our colleagues. With that, okay, Simone, how much depends dimension of field on performance of model? Solveig, is this question for you or someone from your team?
I'm not entirely sure what you mean by dimensions.
Hello. I speak directly. And yes, my doubt was yes the dimension of the plot of the field that you have to recognize the crop on.
You mean the size?
The size, yes. How influence the performance of the model?
Is this about the crop prediction model?
So generally, when you have very, very small fields, obviously you have less pixel covering the field, which usually, if the time series is good enough, doesn't have too much of an influence. But if you have a lot of pixels covering the outside, like covering the area that's not inside the field, you always have a mixed signature within the pixel, which means you don't have just the crop type, but also other kind of information from what's outside the field, which obviously influences the data. But in most cases, the fields that we handle are large enough to not have an issue with this as much as very, very small fields.
Okay, thank you.
Yeah. We have another question from Irene. Generic question: how transferable are the models, physical and AI-based, for instance, to other regions, climate conditions, etc.? Also, given the climate change and extreme weather phenomenon. Thank you for questions.
So the physical models are usually better transferable because they try to represent the physical environment. They are not trained in the sense that AI-based methods are, which ultimately they usually like PROMET or crop growth model. It already receives meteorological information, elevation information, soil information. So it already knows the differences between places and can do more accurate predictions. When it comes to AI-based methods, at least in the crop prediction, yield prediction centers, it depends on how well they generalize. So if you train them on a very specific crop type or on a very specific area, yes, that you might have more trouble with transferability. If you give it enough input data, you will definitely mitigate those sort of issues. And with climate change and weather, so there are very few models that can handle extreme weather, but extreme weather is usually not, well, it will become more and more, but it's usually rare enough to be handled well enough. It becomes more of an issue when we don't get satellite information, for example, due to unusual cloud cover. So we don't actually see what's going on the ground.
I would
Yeah,
also, if you are finished only, I would also take this question.
yeah, feel free.
Okay. Irene is right in asking about the generalizing capabilities of the models. I would talk about the AI models. So we also have a strategy of spatial ensembles to train the models to be specialized for specific regions because different regions have different weather patterns. In that way, we can improve the generalizability. At the moment, what I showed, the model trained over the whole landscape would not be so much generalizable over other countries, but not as good as it is trained on the data in which it is trained on. But the spatial ensemble technique could be used, a specialized model for a given geography. Uh, and the other thing that can be done is when we have a new landscape to do the prediction on, we can take the existing trained model and fine tune the model to that specific landscape and do the predictions. So.
Thank you for your answers. We can wait a few more seconds, minutes to see if anyone else want to ask a question. Meanwhile, Tatiana sent a link for stakeholder inter-survey. If anyone missed the QR code, you can do it in chat. Thank you, everyone. As I said earlier, you can always ask your questions through our STELAR website, through the contact form also. And with that, we will close today's virtual open day. A big thank you to all who joined us, especially to our excellent presenters. The session will be uploaded to our YouTube channel, so you can revisit the recording at any time. And thank you once again, and have a great day.
Thank you very much.
Bye.
Thank you,
Thank you,
everyone. Bye.
everyone. Bye.